your view on QCD matter.
Okay. Thank you very much for this kind introduction and an invitation, and it's a pleasure to be able to talk about the work here. Today, what I'm going to talk about mainly is work that I've been doing with a new student, Aleksi Kurkela, in the past year, and also with Tyler Gorda. But I'll also review some older work. You might have heard previous talks from me talking about how we can use QCD in neutron stars, and made some statements about phases of matter in the course of QCD. And in this talk and in these papers, what we've tried to do is to put these statements on a more robust founding and try to understand what we actually know and what is the role of these QCD calculations in neutron star physics. Okay. But let's start with an introduction. So of course, in this seminar series, I don't have to motivate that studying the phase diagram of QCD is extremely interesting. And of course, colliders have done fantastic job and are doing fantastic job in that. But there is, of course, this region of cold and compressed, cold and dense QCD matter that remains inaccessible to colliders. And for that, in the very past years, we've had a completely new venue to study the extreme QCD matter there. And that has been brought to us by the tremendous evolution and tremendous advancements in observations of neutron stars, starting from radio telescopes to X-ray astronomy, and of course to the multi-messenger astronomy and gravitational waves coming from mergers of neutron stars. And so this talk here will concentrate on the questions that we can ask and answer by looking at the neutron stars here in the low temperature part of the phase diagram of QCD. Now, just to get the orders of magnitude and sizes is right, you know what neutron stars are. They're end products of stellar evolution. They have masses of the order of couple solar masses. They have radii at 10 kilometers. The quiescent neutron stars have temperatures which are low enough that we can consider them as zero temperature objects from the nuclear physics point of view. But it's very interesting that in collisions of neutron stars, the temperatures can go quite high up and start to overlap with the temperatures reached in heavy ion collisions. We don't know how dense objects the cores are. We don't know how large densities are reached. That is, of course, because we cannot peek in and see it. It requires modeling. But they are by far the most dense here, pointing out that we don't know what is there. Do you, by the way, see my cursor? If I move the cursor, do you see it?
Now, no. Try to. Yeah. Okay. Yes, we do.
Okay.
Yeah.
Okay. So we don't know what's happening inside the star, and in fact, we know only out of this radius of about 10 kilometers, we only have a theoretical control on the first 500 meters of the star. So if you can see, I drew here a pink line here, which basically shows where we know that where the neutron star is under theoretical control. So it is really a adventure to try to understand what is here happening inside the core of the neutron star. What's of course interesting about the neutron stars is that the properties of the neutron stars, they reflect the properties of the dense matter. Similarly, as in heavy ion collisions, the collectivity in the events reflect the microscopic properties of QCD matter, equation of state and viscosities and so on. Here, the macroscopic properties reflect also the macroscopic properties of the stars, reflect the equation of state. Whereas in heavy ion collisions, this mapping between micro and macro physics comes through hydrodynamics. Oftentimes here it's the hydrostatics, the competition between the pressure and gravity that transforms the equation of state into macroscopic properties. For example, this iconic plot of the radius as a function of mass. There's a one-to-one correspondence between the equation of state and the radius because of the competition of pressure and gravity. And similarly for many other macroscopic features that I will mention in a minute. So right now we are indeed living in a revolution of new data on the neutron stars that can allow us to try to access the equation of state. Here are radio telescopes, X-ray telescopes, and gravitational wave detectors. From the radio side, what is the most important thing for the equation of state point of view are the discovery of very high mass stars. There are stars whose masses are around 2 solar masses, and they immediately tell us a story about the equation of state, because the equation of state has to be stiff enough. The matter needs to be incompressible enough so that these very massive stars don't become unstable. Similarly, in the International Space Station, there is the nicer telescope, the neutron-star interior composition explorer, that has very recently measured, or at least given lower bounds on the massive on the radii of 2 solar mass neutron star, using a X-ray timing where you look at a hotspot on a neutron star, and because the space is bent around the neutron star, that affects on how much of the time you can see this kind of a hotspot radiating. And of course, we have fantastic gravitational wave detections, and in particular with GW170817, which was a particularly lucky and loud event that gave us bounds and measurement of the tidal deformability, lambda tilde, that describes how much the 2 neutron stars in spiral towards the eventual merger are deformed by the tidal gravitational fields of the binary partners. And all these information, all this data tells us an information about the equation of state. What do we know from the theoretical point of view then? So we know the equation of state from nuclear physics up to roughly nuclear saturation density. That's the density, by the way, which is reached in large nuclei. And these calculations are very impressive. They are brought to high order in effective field theory calculations. You include interactions between nucleons by order, adding the nuclear forces. And what, in my understanding, stalls the advancement to higher orders and more larger densities is the lack of knowledge of the low energy constants that you need when you go to higher order calculations. Indeed, these very impressive calculations tell us about the equation of state up to roughly one nuclear saturation density. Now, from my point of view, I've been working a lot in the perturbative side, trying to come and meet the equation of state from the very high density region using perturbation theory. And in perturbation theory, what you do is you start from gas of free fermions, and then you expand on the QCD coupling. The very seminal work was done already in the 70s by Friedman and McLaren, who computed this equation of state up to and next to leading order, and we've been trying to, in the past decade, improve these calculations by adding mass effects and temperature effects and so on. At this next to leading order, there's two contributions to the pressure. One comes from set of 3 loop diagrams, and then there's another part which I call the soft part here, that comes from an infinite number of diagrams with any number of loops with given topologies, and these are very difficult calculations, and it's amazing what Friedman and McLaren were able to do already in the 77s, resumming these sets. But at some point in 2016, with Aleksi Kurkela, we figured out that these soft diagrams can be written in an effective theory, hard loop effective theory, which simplified the calculation enormously. And with this new conceptual framework, calculational framework, we've been pushing the calculations to even higher order, to next to leading order. Just to give you an idea what the status of the calculation is that we have computed the soft part of the calculation, which is a 2-loop calculation in this hard loop theory. That's completed, and there is a mixed term that was just completed. That's like a correction to the HTL theory, which we completed for QED, not for QCD this spring, and the QCD calculation is coming. The conceptual issues have been figured out here, but there's more to calculate in QCD. And eventually, what is missing here is a for-loop calculation within QCD that will hopefully we will be able to do that at some point. But that's a large calculation, and no concrete promises on the time scale on that. But anyways, that's the status of the perturbative QCD calculations. We hope that we can push these calculations to lower densities at some point, but now they are quantitatively accurate, around 40 times the saturation density. Now, this is, of course, much higher density than the densities reached in neutron stars. And you can, of course, question how useful these calculations are for neutron stars. And I try to convince you in this talk that they are actually very useful. Besides trying to do ab initio theory calculations, there's been, of course, a lot of attempts to understand what's happening here in the intermediate densities, and there's, for example, a lot of different model calculations, NJL models, Waleczka models, ADS-CFT based models, and so on, that make some kind of a predictions on what the equation of state could look here in the intermediate densities, and there are databases where you can download bunches of equation of state like this. This is from Compose database, and I think Veronica will next week talk about these databases more. Nowadays we have all this data that I was describing earlier, and with that there's been a new way of trying to access the equation of states, doing model independent inference by basically creating large ensembles of equation of states, and then trying to see which of them are consistent with the observational data. And I will talk about this particular study here later in this talk. Now, the equation of state is, of course, interesting in its own right. It's a fundamental property of QCD, but it is still just a function. Why I am really interested about in the properties of the equation of state is the fact that the equation of state itself, it reflects the phases and phase structure of matter. And there's a couple of examples of such cases. For example, here is the equation of state of hot QCD matter that you certainly know very well, and you can see a qualitatively different behavior between the hadronic gas and the quark matter phase, and that is encrypted in the equation of state. So by looking at the equation of state, one can know something about the phase structure. Similarly, in the context of neutron stars, if you look at the interface between the outer crust and the inner crust, in the outer crust you have matter which is made out of a lattice of electrons, and nuclei in a lattice with increasing number of the ratio of neutrons and protons, there's eventually a point where you reach the famous neutron rip line, and the matter starts to turn in from lattice of nuclei to nuclear matter, and that transition here you can see clearly in the equation of state. There is a shape there, and that again shows that the equation of state tells you a story about the phase structure. In analogy to these pictures, and one can of course make many of these kind of figures. In a Nature Physics paper a while ago, we interpreted a certain feature that it can be seen in the equation of state that of called QCD matter that has been inferred from the observations together with theoretical inputs at low and high densities. We see that there is a certain feature happening here around the same energy densities where quark-gluon plasma is formed in heavy ion collisions, and we interpreted this change of change in the equation of state as an onset of quark matter. Now, in this talk, I'm not going to go and discuss the details why we believe that this softening here, the equation of state softens here around this energy density. I'm not going to ask questions, or I'm not going to address the question whether or not that should be interpreted as quark matter, but I'll take a little bit step back and ask question whether or not that feature actually is there. So does the equation of state have this softening feature? Is this a robust prediction? And of course, there's the question whether or not if that feature is there, do the cores of the neutron stars reach this softer phase that I previously interpreted to be being as the quark matter phase? So that's somehow the aim of this talk. Ask about robustness of this feature. It's very interesting to see that there's been two ways how to do these model independent studies, and most of the studies are done such that you just extrapolate from the CET, from the chiral effective theory, from the low densities upwards, and you don't include the PQCD constraint into the calculation. And another option how to do it is to interpolate between the CET and the QCD, as I showed in the previous slide. And what is an interesting observation that arises from these calculations is that these extrapolation studies do not seem to see the softening. Here is, for example, an example from Somasundaram and collaborators, where they use only astrophysics constraints and no QCD constraint, and the softening of the equation of state is not visible in their posterior. However, if we add the PQCD and do an interpolation, we do see this particular softening. Similarly, here is a recent result from Altiparmak and Ecker and Retsola, where they see that the speed of sound gets smaller at higher densities. Basically, after this kink here, lower speed of sound reflects a softer matter. So they see the softening in their analysis, and that's an analysis that again uses the PQCD and is an interpolation study. Whereas here is another recent study by Laundrie and Essig and collaborators where they do not see the softening, and this is an extrapolation study. So what we see, there's a pattern forming that these extrapolations do not see the softening feature. Here there's no evidence that the speed of sound is going down. Here there is. And so the extrapolations seem to have the softening feature, but the interpolations do not. And that raises a question to me. is this feature appearing into the equation of state? Is it there because it's a robust prediction of QCD? Or does it have to do with the choices I've made in the analysis? We do this interpolation over 2 orders of magnitude in energy density using piecewise functions that have 4 or 5 segments. Is this coming from the construction itself? We of course have tried to make sure that it is not coming from the construction by increasing the number of segments and trying different functional forms of the interpolation functions. But there's always this question that I feel uncomfortable with, is is it really the PQCD that's giving you this information? Could it really be that this PQCD at 40 saturation densities leaks information down to densities of, say, five times the saturation density? And that's going to be the topic of this talk, and that has been the topic of my student Oleg Komoltsev's work so far. So this is the outline of the rest of the talk. So I will first talk about what non-negotiable robust statements we can make about the equation of state here at lower densities, at neutron-star densities, by using the calculations that are accurate here at 40 saturation densities. And after that, I will discuss how these statements that we can make can be used to help equation of state inference and tell us information about neutron stars themselves. So you can look at this plot here and think that, okay, I can draw any kind of line between the two ends, but that's not true in thermodynamics, and that is also not true especially in relativistic thermodynamics. There are conditions on what kind of functions you can use to interpolate the equation of state. There are, from normal thermodynamics, there's a requirement that the resulting equation of state has to be mechanically stable. So it means that in this EP plane, the function has to be monotonic. That's a flat line here means a 0 speed of sound. And because we're talking about a relativistic system, the speed of sound cannot be larger than the speed of light. So that gives you also some kind of a limiting case. And now you can start thinking, what is the most extreme equation of state that could connect the low and high density limits? And this is actually a game that was played already in 1974 by Rhodes and Ruffini. And you can see that the most extreme configurations that you can do is to first have a large segment of matter with speed of sound equals 1, and then followed by an enormous phase transition. Now, this is of course not in the cards. This cannot be the physical equation of state. We have many reasons to believe that, but that is a hard bound that comes from very basic principles of thermodynamics and relativity. Here is another more recent realization of these similar bounds coming from the stability and causality by Lopeoter and collaborators. These works, however, they do not use complete information that is available. And there's in addition to stability and causality, there's a third point that can be added to the list of these robust constraints, which is the consistency. That's actually an interesting thing, because it comes from the fact that here we are showing the reduced equation of state, the energy density as a function of pressure, or pressure as a function of energy density, which doesn't contain all the information of thermodynamic functions. Unlike the grand canonical potential, and there's more information in the grand canonical potential than in this reduced equation of state. And these microscopic calculations give us the full grand canonical potential. So in addition to knowing the energy density and pressure, we also know the particle number density and chemical potential, for example. And now you can ask, well, if I have an equation of state like this, very extreme equation of state there. Looking at the EP plot, it looks like that's a completely fine equation of state, but there is no construction which would have this equation of state and be able to connect the particle numbers or the chemical potentials at these two limits. So there is more information available than is used in these constructions. And that's exactly what we started to understand and try to understand with OLED. The most convenient way to impose all of these constraints to the equation of state, we figured out that it's instead of looking at epsilon versus energy density versus pressure, it's more beneficial to look at the baryon number density as a function of baryon chemical potential. And so here in this plot here, the chiral effective theory limit is here, PQCD limit is there, and we start to ask what is the space of functions that we can access without violating these thermodynamic constraints that we have available. And so in this space of density and chemical potential, the stability tells that the interpolation has to be monotonic. Causality tells that there's actually another slightly larger minimal gradient for this equation of state for this line that depends on n and mu. Probably this line that I draw here by hand probably would violate it because there's a quite flat quotient. And furthermore, the consistency of all thermodynamic variables can be imposed by looking at the integral under this curve. So the integral under this curve is given by the pressure difference of these two limits, and that we know from the microscopic calculations. And in this case, it's roughly 1/3 or 40% of the area under this curve that you have to have. So that fixes the area under the curve here to be being roughly 1/3 of this square. And these are now the rules of the game that we started playing. To make it somehow visualize these constraints, we figured out that it's nice to plot this causality constraint here, the minimal slope of the equation of state as a vector field here. So in any point where your equation of state is, the slope of the equation of state has to be at least this. It can go directly up, vertically up, which would mean that there's a phase transition, and it can follow the arrows, which means that's a equation of state with speed of sound of 1, but it cannot be below, because if it's below, then the equation of state would violate causality. And now you can see that in this space of density and chemical potential, there are regions that just cannot be reached. If you start from this point and try to use a causal equation of state, you can never reach this region here. And similarly, if your equation of state somehow happens to wander here, you can never reach this point with a causal equation of state. So those regions can be ruled out non-negotiably. But and this corresponds to the limits of Rhodes and Ruffini. But there is more. We can ask at any point here, take any point in this two-dimensional plane and ask what are the minimal and maximal areas under the curve for a curve that goes through that point. So what are the minimal and maximal pressures that can be obtained for an equation of state that passes this point? The minimal pressure comes through this kind of a construction where you follow the maximally stiff equation of state and then have a phase transition and maximally stiff equation of state and then a phase transition. That's of course a completely crazy equation of state, but in principle, that is still possible. There's no fundamental reason why it would not be possible, at least known to me. And so that tells me what's the minimal pressure, and this line here, this green construction, tells me what's the absolute maximal pressure that can be reached for an equation of state that goes through that point. And it turns out that there are regions here that if you end up in, then it is you are forced to have too high pressure, and that's why they are excluded. And if you are in this region here, then you cannot have enough area under the curve, and that's why you are excluded. So that constrains this. This is the way how we can use this thermodynamic consistency to further exclude equations of states. Now, this whole thing, you should actually think it in terms of 3D volume here. This is now putting the pressure, allowed values of pressure here in the z-axis. If you look at this from above, that resembles the picture on the previous slide. And so the equation of state must somehow be inside this volume. And if it goes anywhere close to the edges, it has to do something very drastic. And now once you have this 3D volume of allowed equations of states, you can start taking projections and slices of this to make predictions about, for example, the plane of energy density and pressure. Here is a prediction coming from this, showing the extent of this new constraint that we call an integral constraint, which shows that there is regions here and here which were not previously constrained, which are not constrained by just considering the stability and causality as previously. And so that tells us how the information about the PQCD calculation seeps into lower densities. And it's actually quite remarkable that you get a non-negotiable constraint from the PQCD calculation already down to around 2.2 times the nuclear saturation density. This calculation perturbative calculation is done at 40 saturation densities, and it constrains the equation of state at 2.2. That's very powerful. And that is there because of the rules that you have, how you can make a thermodynamically consistent, stable equation of state. I think this result is somehow most dramatically shown by also adding in the density information, so the number density information here, because the projection on the EP plane does not tell you the whole story. And here you can see that these fun shapes here, they are the allowed regions of energy density and pressure for a given number density. So this one here is for 2 saturation densities, this one is for 3 saturation densities, this for 5, and this for 10. And the blue area is the allowed region. Sorry, now I said it wrong. The black region here, the outline here, is the region that is allowed without PQCD. And you can and the blue region is the region that's allowed with QCD. And so you can see that at 2 saturation densities, there is no constraint coming from the PQCD calculation. But already when you go just to 3 saturation densities, there is a region here which is excluded by QCD. And at 5 saturation densities, this is much larger. And at 10 saturation densities, only a very small portion of the values of epsilon and p that would be otherwise allowed are allowed once the QCD constraint at high densities is imposed. This is a log plot, but if you look at these areas that are allowed or excluded in linear scale, this here 95% of the area is excluded by QCD, and only 5% remains. So it's a quite dramatic effort. Now you could ask, and that is just by imposing these fundamental physics principles on the equation of state. You can of course ask if these equations of state that we are excluding are somehow completely out there. They are too crazy that nobody would have ever suggested something like that. And in order to see if that's the case, Oleg went and downloaded these equations from this Compose database and checked whether or not they are consistent with the perturbative QCD limit. And as you can see, all of them are, of course, consistent with the new constraint at low densities, but all of them become inconsistent with QCD at some point. And so that tells you that this constraint that we are giving here is actually it does have practical use, and it can be used to exclude these models, for example. Okay. So let me summarize the first paper that I was talking about. So the key points here are that the triplet, the density, pressure, and energy density, that carries more information than the reduced form of the equation of state, pressure as a function of energy density. And that can be used, and one can show analytically that the calculation that is done at 40 times the nuclear saturation density offers a robust constraint down to 2.3 times the nuclear saturation density. I think what's interesting also about these constraints, and I think that was the original motivation by these people, very interesting, is that these constraints that I'm giving here, they're purely theoretical. They're independent of any neutron star observations or their modeling, and also they are completely independent of assuming general relativity. So this kind of constraints can be used as a starting point of any BSM or beyond GR studies. These are completely independent of astrophysics. But the question that still remains open, and I think it's very interesting, is that we offer some constraints from PQCD, but do they offer additional information to neutron star observations, where these equations of states that we are excluding, were they already excluded by our observations? Are these constraints, are they complementary to neutron star observations? Are they consistent with neutron star observations, or are they perhaps in contradiction with neutron star observations? Which of course could be the most interesting case. And in order to do so, we need to have a framework where we can model these stars all the way the surface to the core, and then make predictions on the neutron star properties that we can then use to constrain these equations of states. And that's the part two of this talk about this plot and a framework that we constructed using the previous paper to study the effect of QCD for equation of state inference. So the idea was to have a equation of state inference setup, a Bayesian setup, where we can turn on and off the PQCD constraint to observe what is the added information that it gives us. And so we did that, and we wanted that to be, we wanted to also present the constraints that I talked so far in a way that can be used by other people in their own inference setups in a simple way. And so what we didn't want to do is to have a interpolation approach, because that requires that you impose the QCD constraint already from the beginning on creating your prior. But we wanted to use this region here at 10 saturation densities to constrain our prior after the. So what we do is we do an extrapolation here of the equations of states, and then we can either impose that the equation of state has to land on this area at 10 times saturation density, thus imposing the PQCD constraint, or not, and we can see how this works. Now I have some details on the framework here, I know that many people are working on Bayesian analysis, so perhaps some of these details are interesting. So what we do is we first generate a prior set of equations of states using a Gaussian process regressor. And what we do is we perform the Gaussian process for an auxiliary variable that we call phi, which is related to the speed of sound. And the reason for this change of variables is such that the speed of sound is constrained by construction in the range between 0 and 1. And this auxiliary variable will be drawn from a Gaussian process. If you don't know what the Gaussian process is, that's fine. It's basically correlated random numbers, which has two parameters. One is the correlation length, which tells how rapid wiggles you can have here, and there's a variance that tells how large these wiggles are. And we construct, using these Gaussian processes, a hierarchical model where we also draw these means and variances and correlation lengths from distributions from themselves to avoid any bias in making this prior. Here is an example of few samples of our prior, which have been already conditioned to have the correct behavior at low densities. And you can see that they're very versatile at higher densities to have all kinds of functional forms there. And once we have constructed our prior, we condition the prior with the likelihoods that we get, and the data that we use is the data that I discussed earlier. We use the mass measurements from radio telescopes, and we use the mass radius measurements from X-ray telescopes from NICER. So these come from pulsars, and we use the information that we have from the tidal deformability coming from the GW 1708717. And then this is all quite standard, following many works in the field. In particular, we are quite closely following the work of Laundrie and Essig. The main difference is that this auxiliary variable is for us as a function of the number density instead of the energy density, so that we can impose our constraints. But the thing which is the new point is to then also add a likelihood function that comes from the PQCD and tests whether or not the equation of state extrapolation that we have created can be connected to the PQCD using the construction before. So basically asking, are we inside this diamond shaped region here? There's a small detail that I did not discuss when I discussed about the perturbative calculation, which is that the perturbative calculation itself contains uncertainty. Like any perturbative calculation, there is a scale variation uncertainty, and here what we do is we have a Bayesian interpretation of that scale variation uncertainty coming from ways that these scale variation uncertainties are dealt with in high energy physics, and so the diamond shape here that I showed in the previous slide is the red one here, but there's a little bit of leakage out of that shape because of the scale variation uncertainty of the results. Here are a few more details about the scale variation uncertainty. So what we do in practice is that what we need from QCD is the triplet of the pressure, number density, and chemical potential at some given chemical potential in this case. And if we have chosen the renormalization scale, and the chemical potential. Perturbative QCD gives us a prediction of the two other variables. And indeed, then we follow a scale marginalization interpretation of these normalization scale variations to form a probability distribution, a Bayesian probability distribution of the PQCD result at these high densities. And we marginalize over the renormalization scale with a logarithmically uniform distribution. And then once we have these things, we can ask the question whether or not for that we can reach the PQCD at the endpoint of the extrapolated equation of state. That's we've extrapolated up to 10 times the nuclear saturation density, and that gives us a Bayesian weight of that particular equation of state. So now we can go to results. Here I show the prior, which is the set of these blue set of these lines here. That's a small sample of some 10,000 equation states drawn from the prior, and then they have been colored with the Bayesian weights that come from either the pulsar observations, so that's the mass observations and the mass radius observations from NICER, from the gravitational wave observations, or from QCD, using the tools that I just described. You can see that the pulsars, they require that the equation of state is stiff enough, goes fast enough up here, so that you can support these two solar mass neutron stars. Whereas the gravitational waves, they tell you that the equation of state has to be soft enough at low densities, so that the effect of tidal deformability is not too loud in the observed gravitational wave signal. And lastly, what you see is that from QCD, the QCD, it is not possible to connect to the QCD at 40 saturation densities if the equation of state is too hard at these rather high densities. And so that is the constraint that we get from QCD. It softens the equation of state at high densities. And it's quite interesting how all these inputs that we have here, they are very complementary to each other. This Venn diagram here shows the overlap of the different posterior distributions after imposing different combination of these equations of states. You can see that just the pulsar measurements, they cut down our prior by a factor of 2. Roughly half of the equations of states are allowed after imposing the pulsar observations. Similarly, the gravitational waves and for the QCD. And you can see that the overlap region of these three different sources of information is very small, because they cut different sets of equations of states. So they are very complementary to each other. Now you can, of course, put all of this information together and make then predictions posteriors of the various properties, such as the speed of sound in the neutron star, or the equation of state, or the macroscopic properties of the neutron stars themselves. And now, what is the really interesting question to ask is what is the effect of this QCD? If we turn the QCD constraint on or off, what happens to the equation of state? And here you can see that here are some confidence limits coming from the previously shown posterior. You can see that the posterior favors harder equations of states at high densities. That's the violet band here. But when if you don't include QCD, but upon inclusion of the QCD information, the equation of state softens dramatically, and you see the softening feature that was seen in the interpolation studies, but not in the extrapolation studies. You can see that if I don't add the QCD, I get a very similar shape to the extrapolation study here. Whereas when I add the QCD information, I get something which is very similar to the equation of states that we get from the interpolation studies. So the conclusion here is that the softening really is caused. It's a prediction. It's a robust prediction of QCD, and was not coming from the interpolation over 2 orders of magnitude. Softening is a prediction of QCD. This is of course also seen in different in other observables. So for example, you can look at the speed of sound, and again the blue region here shows the posterior without QCD, and it shows very similar behavior to the studies that are extrapolation studies. There is no constraining power at high densities in either of these cases, but when QCD is imposed, you see this peak structure forming, which then at higher densities ends up at lower speeds of sound. And this softening happens within the density range that is reached from in maximally massive neutron stars. And again, this posterior looks very much like the posterior here from an interpolation study by Wetzel and company. So again, the softening is indeed caused by this QCD input and not by interpolation. Now, so the QCD input seems to be very complementary to the equation of state, to the astrophysical observation. So you can ask, is this then something that you can test? It's of course nice to have a theoretical prediction, but it has to be, but you would of course want to test. But to the extent that something is complementary, it's something that you don't see in the data. And so what one would really like to have is a prediction from the QCD that you can test in time. And it turns out that we have something like that. When you have a neutron star merger, 2 neutron stars coming together, there's 2 possibilities for the final binary merger product of this process. You can either end up having a black hole, like there's various ways how that can happen, or you can have eventually as a final binary merger product a neutron star. And we saw that adding the QCD input to the equation of state, it makes the equation of state softer for higher densities. And because of that, it tends to destabilize the stars because it's more soft, it's easier to collapse into a black hole. And we saw that without the QCD input, the probability, the posterior probability of forming a black hole is roughly 50-50. There is no theoretical prediction coming from the other astrophysical data on what the binary merger product should be. But once we include the QCD constraint, we have an overwhelmingly strong constraint that the final binary merger product has to be a neutron star, black hole instead of a neutron star. Now, this conclusion is consistent with the current modeling of the electromagnetic counterpart of the GW 170817. These different scenarios lead into different electromagnetic counterparts, but that requires a lot of modeling of the post-merger product and the jet and the accretion disk and so on. So there's lots of modeling assumptions here. But here from QCD, we get a crisp prediction that indeed most of the binary merger products have to be black holes, and I find that very interesting. And we will see this of course tested in the future. Okay, so let me then conclude with my second summary. the QCD input should be included in any neutron-star equation of state inference setup because it really impacts the results. There's been other studies like this one here, which conclude whose results on ballpark agree with what I showed here. It is the QCD that drives the softening, which I interpreted as a transition to quark matter around 750 MeV over Fermi cube density. So that's the density roughly where also quark-gluon plasma is created in heavy ion conditions. And these results, what I'm showing here, they are consistent with the previous non-Bayesian interpolation studies that I mentioned. We have a prediction that QCD implies that most mergers lead to black hole formation. And of course, now we hope that this information about the QCD calculation will be implemented in any complete inference setups. Now you can condition your prior with QCD, and that's because Oleg has made this nice Jupyter notebook publicly available for GitHub, where one can use this QCD, the likelihood function at ease. Okay, so that's it. Thank you for your attention.
Yeah, thanks a lot, Aleksi, for fantastic, exciting results. And also perfect timing, really. It's 4 p.m. without 20 seconds, so great. So I see already the first hand from Nu. Nu, please go ahead.
I actually was trying to applaud, and I hit the
okay. Okay, now you need to ask the question.
But yes, sure, I can. Yeah, thank you, Aleksi, for the very nice talk. I have a question that imagine, just on your conclusion, imagine QCD prediction is different for the softening part. What would happen? You know what I mean? The answer maybe is in your setup. So that's my. Or in other words.
So yeah. So you're asking, what if QCD would contradict the observations? Right. Well, the observations themselves, they have a lot of modeling uncertainties that come from different ways how the data is treated. So of course, the first question would be, is there questions in different observables that should be taken care? But of course, we trust our observational colleagues to have everything under control. And if it happens so that at the end of the day, everything is taken into account, and there is still an inconsistency, that means that the assumptions that go into this business are false. What are the assumptions? The assumptions are that the neutron stars are described by general relativity and quantum chromodynamics. And if one of those is not true, then the equations then all of these different observables don't need to be consistent with each other. And so that is an inroad to using these neutron stars as a tool for physics, for fundamental physics beyond standard model and general relativity. So that's of course the big hope that we will see this inconsistency happening at some day, but we haven't seen that yet.
Yeah, if I may, I have two. It's not follow-up related. Tatiana, can I just?
Yes, let's move on. And I think also from Deepak there is a related question. So let's focus on this topic. Go ahead, Nu.
Yeah, the two things I maybe I missed. One is in the QCD part of calculation. Does the gravitational interaction included? This is one. Secondly, for QCD calculation, to what flavor you included? For example, only light quarks, S quarks, charm quarks. Are those in the calculation? Maybe it's not important, but I just
these are very good and easy to answer questions. So first of all, the gravity is not included in the equation of state calculation, just because the effect is so small that you won't see that won't change the results. We use three flavors: up, down, and strange And at the densities at which we use the calculation, we've seen that the strange mass effect is so small that it is numerically not needed. We have the strange mass included to the next to leading order calculation, but not in the next in the partial next to leading order calculation that we use now, because the higher order correction is much larger than the mass correction.
In the
so three flavors of massless quarks.
In the literature, there are lots of discussions, not now, even for a long time, strangeness will soften the equation of state. But you say here it's not really.
That's right, and no, that's completely true. But that effect happens only at lower densities.
Oh.
We are using this QCD calculation very far in the asymptotically high densities at 40 saturation densities, where this effect is very, very small. And we are using this construction of finding what is the most general space of functions to go down. So if you were to take the equation of state and extrapolate the QCD result to regime where it's not really under quantitative control, take it as a model if you wish, then completely agree with your statement that the strange mass would affect the equation of state.
Thank you.
Okay, thank you. Let's move on with the question from Szabol Borzani.
Hi, Aleksi. Thank you for a nice talk. So a question to one of the last slides, when you make this post-diction that there was a black hole as a result of the merger, the GW of 17. So can you tell which part of the equation of state is responsible, whether you have a black hole in the end or you get some post-merger signal? So it would be very nice to have some post-merger signal, but what are the chances? So what is the equation of state? What part of the equation of state has to be different to get something, but then in the black hole or a black hole immediately?
So I mean, this is determined by the highest densities that you reach in this post-merger star, and those can be higher than the equation of state in the 1.4 solar mass neutron stars that might be colliding. So the density range that you get, that you are observationally sensitive, gets higher in this post-merger. So it is roughly the equation of state at the densities reached in a 2.4 solar mass neutron star or so. Does that answer your question? I'm not sure if I answered your question.
Yes, I think it kind of does. So I have to look at the large. So whether we see post-merger signals, would it already tell something about this fact, whether we see that, about a high density part of the equation of state? Would it allow you to constrain more? Just the fact that it confirms your...
Right, absolutely. So if we were to see the post-merger signal, that would of course tell us about the densities reached in the post-merger, and that would give us a wealth of data about the equation of state.
Or even the absence of the post-merger, right? The absence of the post-merger signal would also constrain, because it would confirm your expectation. It has to be a black hole at that density.
Well, black hole also has a post-merger signal, but the usual idea is, of course, that you form this hypermassive neutron star that rings for a while until it decays into a black hole.
Okay.
Okay, thank you.
And of
Let's
course, that ringing
on.
would be fantastic.
Yeah. Or a few more of neutron star merge events, right? Yiyan, please, your question.
Yeah. Thank you so much, Aleksi. Maybe my question is naive, but my question is, given the current constraint, is the color superconducting phase consistent or compatible with the current constraint?
That's an interesting question. The thing with the superconducting gap is that it doesn't affect the equation of state strongly. So it is because it happens at the Fermi surface and not that the equation of state gets contributions from everywhere in the Fermi sphere. And certainly at these densities that we're talking about, that would be a very small effect. So I would say that anything, the question is if we are in the quark matter phase, what is the transport phase there? Are we in a color superconducting phase or not? We don't have the sensitivity to that. The questions about that should probably be answered by looking at neutron-star cooling and things that involve transport. It's very difficult to access that directly from the equation of state, but it's a very interesting question. We are not in contradiction in any way, but I have no way of knowing if there is color superconductivity at this point.
Thank you so much.
Mm-hmm. So I suggest we move on with the question from Deepak. Deepak, would you like to ask your question directly, not via chat? Otherwise, I will just read it. Deepak? Okay, so then let's just look at the chat. So it's kind of follow up, but not on the color superconductor, but on the quark-ionic matter. Can we consider quark-ionic matter near the crossing point of the extrapolated lines?
I mean, quark-ionic matter is one of the models that are available there. I don't know what the microphysics in the interpolation is. I'm not sure if I understood what the question about the boundary was. Can you repeat?
Yeah, okay. Yeah, so we have the question in the chat, crossing point of the extrapolated lines. I don't know, maybe one could pick up one of the figures with variety of the equation of state. I don't know, Deepak Kumar, you are here, so I don't know if you can speak. But yeah.
Hello.
Yes, we can hear you. Hi.
Okay, so thank you for the talk. So my question is regarding the quark-ionic matter. So there is some paper by McLaren. He showed in the core of neutron star, in the presence of quark matter, the sound velocity decreases. So in this scenario, we also have seen the sound velocity as decreases as we include the perturbative QCD. So can we think the quark-ionic matter in the region where we interpolate the region?
So what you're asking to me is, are these results, these data-driven results that I have, are they consistent with quark-ionic matter? This I don't know. You have to ask people who do quark-ionic matter. But what I see is that they are consistent at high densities with PQCD type quark matter. And if it is so, and I believe it is, that quark-ionic matter models predict some kind of peaks, or posting some kind of peaks in the speed of sound, and then coming back, then yes, that is the behavior that is there. But this is a data-driven, model-independent way of looking at it, and I cannot tell you if a specific model. I mean, I can see if this is consistent with specific model, and if you give me an equation of state, I can compute its likelihood value. but I don't know if this is a particular evidence for quark-ionic matter. I wouldn't maybe think so, but it can be consistent with that.
Okay, thank you.
Yeah, thank you. So we move on with Jimin-Ko, please.
Thank you. I have a few questions. Let's start on a simple one. In your conclusion, you mentioned the matter converted to quark matter at 750 MeV per cubic Fermi. So I would, if that's the case, I would expect in heavy-ion collision at the CIS for the hardest experiment, center of mass energy around a little bit above 2 squared S2 GeV, one can reach baron density maybe 2 and 2.5 normal density. So that energy density will certainly exceed the critical energy density for phase transition to quark matter. So if you take the conclusion seriously, that means quark matter already formed in heavy-ion collision at the cis?
Mhm.
Okay, that's good.
I like it also. Nobody
I-
disproved.
The reason is most of the transport that was starting collisions at the cis energy, nobody including QGP phase, as far as I can recall, right? We're only including one. So if that's the case, we really need to include in the platonic phase, then to see what observable one should look at in order to see these phase transitions. So if your conclusion is good, is right, then it's very exciting. Even we can study dense quark matter at cis.
Yeah, I think that's a very interesting point. And I agree, and I take the conclusion seriously. The thing here, though, is that I'm not saying that there needs to be a phase transition. It could be also a crossover transition. So it might be that it is difficult to find the observable effect, but that's of course a matter for the theorists, and of course that should be done.
I continue with my second questions.
Yes, please go ahead.
Okay.
Also, I would
Yeah,
have.
the second question is, you use PQC to calculate equation of state at very high density, 45 normal Newton density. And then for the low density, you use Chiral effect theory and other phenomenological models. And all those models, you can extract the too high in density. It's possible to parameterize the results from your PQC calculate extreme high density with NGO type of models to determine the corrections. Then extrapolate that to the lower density. Is that
okay. So let me
valid
unpack
a question to ask?
Okay, let me unpack some points from that question. So first, you said that the chiral effective theory is a modeling approach, but I would rather call it an effective theory method, because you have a power counting and you have low energy constant. So you're kind of, it is not just a model, I would say.
Okay, I agree. Yeah.
And could you parameterize the PQCD within NJL? Yes, you could, and you could say like if you that goes to the category of questions of what kind of interpolation or extrapolation functions should we use in these intermediate densities. So what we've done,
I use just high density. Exactly use your equation of state. I fit by NGL types model. Of course, with the normal NGL model, probably that won't work. Can I add other terms, right, with higher order terms to fit your equation of state? Then I can determine those corrections in those high order terms. Then I can extrapolate to lower density.
Right.
So instead of extrapolate from lower density to high density, I parameterize it with NGL at a high density, extrapolate to a lower density.
Yeah. So as I was saying, that this goes to the question, to the category of questions of what kind of interpolation or extrapolation functions I want to use. We, in doing these model independent interpolations, what we've used is we used piecewise polytropes or piecewise linear functions of speed of sound. In this work that I talked here, I extrapolated using a Gaussian process regression, but you could equally well take as your basis functions some models and hopefully make sure that they cover enough function space so that you are not biasing your results with that model, or maybe that's exactly what you want to do. So yes, you can take models and try to find best parameters using the two limits and the intermediate values, but that's a model dependent approach. Here the point was to have a model independent approach. And I'm not saying in any way that there's anything wrong with the model dependent approach. It's just a different approach. But you can't.
The reason I'm asked this question is when people use a NGL model, sometimes we want to introduce vector interactions, GV, there are some people, they are against that introduction of GV in the NGL model because from lattice calculation of the baryon chemical potential 0, the quark number susceptibility somehow exclude the existence of GV in NGL model. Now, if I can use NGL tablet to fit your PQC with a very high density, I can see is GV allowed or not allowed. You just use the GS scalar interactions or with high order term. Can I reproduce the equational state at a very high density? Do I need additional repulsion? Even your equation is very soft. Do I need additional repulsion?
I don't have the expertise to say anything specific about the NJL, but what you can do is you can use the information either at PQCD at the asymptotically high densities, or you can also use the construction that I described in the first part of my talk to fix some model parameters of yours. And that would be the way I would proceed.
Okay, thank you.
Yeah, so I do not see the hand, but I would like to follow up on the previous discussion on possibility of having some new phase of matter at cis-18 beam energies and what are the observables. I think, Jiminko, you calculated yourself 2018, right? What are the possible effects that one can see in the dilepton spectra if you have first order phase transition or not? And it would
yes,
be beautiful.
I did a long time ago. Yes.
Yeah.
Right.
Yes, but I'm referring to this more recent paper where you look explicitly in the spinodal phases and how exactly the trajectory of the system will go, and then you predict factors 2 to 3 more dilepton yields in the spectra. So it would be beautiful to calculate this observable as a function of different collision energy, to see, yeah, like effect of this phase transition in the scan for different energies. And then, of course, it's up to experimentalists then to verify this in the experimental, in the experiments. So would be nice guidance.
Yeah, great. Yeah, for the dilepton, we haven't done any realistic calculation. I think that was mentioned in our paper 2000, many years, couple of years ago. Do a very schematic calculation. I think even in the indeed there will be enhanced dilepton production when there's a phase transition, especially if there's a first order transition and the density fluctuations in the platonic matter. Then because from QQ bar annihilation, automatically you get enhanced dilepton production. The quark matter density is not uniform. Yes, that's so right. That's true. Yeah. Actually, another observable we are trying to publish is if that's a first order transition at the squared S equal to about 3 GeV or so, that's probably close to what the GSI energies. One can look at the states. There's instability can lead to density fluctuation. Somehow, if the density fluctuation can survive in the ground phase, then one can see the enhanced production of light nuclei like a deuteron, triton, particular triton. So at least I think one of our preprint, we showed the 3 explode at the 3 GeV, that's the first of the phase transitions, then the triton number, the proton number divided by deuteron number square will be enhanced by factor 2 or 3, factor 2 or 3. Right.
I think
so
we
that's
should,
another possible.
I think we should schedule a seminar for Chen-Ming so he can lecture on that.
Okay, so let's move on with the next question from Nu. Nu, please.
Yeah, Aleksi, if you don't mind, I have another question from this. So in your first summary, or before your first, can you go to your first summary? You said QCD is relevant, is predicted the equation of state, which is okay. But if you go maybe 1, 2, go further. You had a plot of equation of state for 3 different positions: QCD, gravitational wave, and pulsar. It's 3 boxes.
The likelihood functions.
No, it's not this one. It's the 3. Yeah, this one. So the left one is a QCD calculation, and the right one is pulsar. You see, yep. Is it right in QCD calculations? Both, I would say, softening and hardening is allowed, right? If I follow these red curves, you see this red allowed region. Really, the constraint is coming from the pulsar. Is that right? The changing, softening equation of state, because the curvature changed. In QCD, it's all allowed.
So what QCD tells you that the equation of state has to be moderately soft at high densities, whereas the pulsars tell that it has to be quite stiff at low densities.
That's
and
right.
I think the characteristic peak in the speed of sound comes from interplay of these two effects.
Right. So
the pulsars make you go up, and then QCD brings you down.
Well, if you go back to the pulsar, also says softening in a higher density region, right? If you above, this part, correct?
Yeah, that is true, and that's that is true. There's a little bit of a overcounting here, though, which is a technical detail related to the mass. So I skipped a detail that you have to also include the prior for the mass distribution of the stars, and if you have a uniform prior, then there is an issue that in order for any star to have a mass, you need to normalize that prior, and that leads into a effect of suppressing equations of states that have very large TOV mass. There's a little bit of a discussion in the community, I see, whether or not this normalization factor that leads into this should or should not be included into the prior, and that slightly suppressing factor here for very hard equation of states in pulsars, and also here in GW170817 comes from this particular fact. We included this normalization factor in the analysis because it drives the same direction as QCD. So in order to be as conservative with respect to the question, does QCD give you additional information? That was the most conservative thing to do. If we're talking about what's the most conservative thing to constrain the equation of state at the end, I think the opposite choice would have been right. But so what I'm saying is that in the case of these pulsars and GW170817, especially this very high density suppression comes from a choice of prior for the mass distribution of the stars in question.
Okay, thank you very much.
Yes.
Can I
There,
ask a short questions? The training here.
yes, if you fix your microphone would be even better. We have some constant noise. We cannot follow you so nicely, Jimmy.
Oh, I see.
Maybe you can move
Yeah.
a little bit further from, there's some.
Can you hear me?
noise.
Can you hear me now?
Yes, yeah.
My question is very simple. It's possible to see your first few slides on the QCD calculation, that formula, right? The energy from the Fermi gas model plus alpha S correction, alpha S square correction, and so on. Yes. How important are the contribution the high order term compared to Fermi gas equation? The high order term make it softer or stiffer compared to the Fermi gas?
Make it a little bit softer.
I see.
Yeah, the way where the corrections make the most important contribution is maybe not so much on the size of the correction. The corrections are actually very small. The corrections are in the 20% range, but the scale variations are large, and that makes so basically the power of this calculation is to know where you can rely on the calculation. By knowing these higher order corrections, we can ask questions like where we have apparent convergence and how far that convergence is there. So the effect of these calculations is to push the region of validity to as low as possible, but not any further than that. If you just have the Fermi Dirac, then you don't know at which point the corrections are actually large. I don't unfortunately have a slide here about the results, but the results look very similar to the finite temperature case where where the behavior is
okay.
about 20% from Stefan Boltzmann until you blow up. And what we are trying to see is how far we can really push that down. And maybe that 20% effect here is not that important, but it's a question of how far we can extrapolate, or how not extrapolate. What is the reliable range where we can use it?
Thank you.
Okay, thank you very much. Are there further questions? 1, 2, 3, 4, 5 seconds. Wait, no hands up. So then, Aleksi, thanks once again for a fantastic talk, very clear. And we are after the phase transition at CS18 energies. We got the homework today. So let's try to verify things. Okay, so with that, I just would like to pass the word to Xiaofeng.
Yes, thank you. Thank you very much for this nice talk, and also Tatiana for this chair the seminar. Yeah, I think that's the end of this seminar, and thank you for the participant. See you next week. Goodbye.
Thank you.
Thank
Bye.
you. Bye.